Okay, so let's do this example. Let's figure out what is the limit as x approaches infinity of the natural log of x squared divided by the natural log of x squared, which are not quite the same function. They are compositions of the same functions, but the compositions are backwards. This one, the square is only on the x. This one, the square is on the natural log of x function. Okay? So, first step in any of these problems is I want to figure out, well, what's the form? Is this in indeterminate form? And if so, can I apply L'Hopital's rule? All right. So let's see. Natural log of x, as x approaches infinity, then I am going to get the natural log of something that's getting bigger and bigger and bigger. If you recall, the graph of the natural log looks something like this. And as x approaches infinity, the function approaches infinity. So as the input approaches infinity, then the function natural log approaches infinity. Very similarly, as x approaches infinity, the denominator approaches infinity, therefore the denominator squared will approach infinity. So I can apply logic to that and say, well, this is the infinity over infinity form. It's another one of those indeterminate forms for which I am allowed to apply L'Hopital's rule. So that is enough to say, well, I can then write this bottom function as g of x. I can write that top function as f of x. I can find the derivative of each, and I then can apply L'Hopital's rule. F prime of x, I will need to use chain rule to determine the derivative. Outside function is the natural log of x, so it's equal to 1 over whatever's inside that natural log, which is x squared, times the derivative of x squared, which is 2x, which I'm going to simplify. 2x over x squared is 2 over x. Okay? G prime, I'm again going to need to apply chain rule, but the outside function is the square portion of this. That's the outside operator. So g prime equals 2 times the derivative of whatever's inside the function, which is natural log of x, all that raised to the 1 power, times the derivative of natural log, which is 1 over x, which I'm going to rewrite as 2 natural log of x over x. Okay. So now I'm going to bring back this limit. That limit has the same value as the limit as x approaches infinity by L'Hopital's rule of the derivative of the top, which we said was 2 over x, divided by the derivative of the bottom, which we said was 2 natural log of x over x. I'm going to simplify that before I apply the limit. This is equal to limit as x approaches infinity of, I'm dividing a fraction by fraction. I can rewrite that as multiplication by the reciprocal. So that gives me 2 over x times x over 2 natural log of x. I have some things that cancel nicely. X is on top and bottom, 2 is on top and bottom, which is equal to the limit as x approaches infinity of 1 over the natural log of x. Okay, so I have applied L'Hopital's rule and I have simplified. Now I have to ask myself, can I directly evaluate? Well, what form is this in? The form of this is, let's see, I have a constant on top, which is 1. over the limit as x approaches infinity of natural log of x, which again leads back to this graph on the top right. As x approaches infinity, natural log of x also approaches infinity. So it's 1 over infinity, which I know is 0. I know how to evaluate that. Therefore, I can evaluate this limit. Limit as x approaches infinity of 1 over natural log of x is 0. Therefore, the limit as x approaches infinity of this original function, natural log of x squared over natural log of x quantity squared, is equal to 0. All right. So we saw one of the infinity over infinity forms there. Now let's make an observation. Let's observe. If I wanted to find the limit as x approaches infinity of that same function, natural log of x squared over natural log of x squared a different way, I might notice algebraically that this top function, I have the logarithm of something raised to a power, which by my rules of logarithms, I can bring that power to the front of the logarithm. So this becomes the limit as x approaches infinity of 2 times the natural log of x over natural log of x squared. Okay. And now natural log of x squared just means natural log of x times natural log of x. So I have a natural log of x on top, 2 natural log of x's on the bottom. So by that, I know that one of those natural log of x's will cancel. I can divide the top and the bottom by it. So that gives me the limit as x approaches infinity of 2 over the natural log of x, which again has the form, I have a constant, which is 2 over natural log of x as x approaches infinity is infinity, which is also 0. So I did not necessarily need to apply L'Hopital's rule to find the value of this limit, but I could if I wanted to. It turned out, if you remembered the algebra, it was actually easier to apply algebra here. So I recommend that if you can apply algebra to find the limit or previous methods, then do so. But that will not always be possible.